So welcome to the final video in our series for aqueous systems. This section I'd like to call section 2 because that's how I would teach it as the second section. And there's three main concepts we need to cover today. There's solubility product converting to solubility or back again. Number 2, predicting precipitation, which is the relationship between ionic product IP and the solubility product KS. And then the third thing, which is probably the trickiest of the three, is the common ion effect. So if we just start off with some definitions for KS and S. So section 1, KS and S. Well, KS is known as the dissociation constant for a sparingly soluble ionic compound. So KS is the dissociation constant. Dissociation. So we're talking about dissociation as opposed to a reaction here. The salt, ionic salt, simply dissolves in water. So it's the dissociation constant for a sparingly soluble ionic compound in a saturated solution. Saturated solution is very important to mention, otherwise we can't do any of the calculations that we do in the next few minutes. So KS is known as the dissociation constant. It's also referred to as the solubility product, also known as solubility product. It may get a little bit similar after a while, so you need to be really clear of which one you're dealing with. So KS is also known as solubility product, and it's the dissociation constant for a sparingly soluble ionic compound in a saturated solution. In simple terms, it's a measure of how good an ionic solid is at dissociating in water. How good is it at dissociating? So the larger the KS, better at dissolving or dissociating. But the larger the KS, the quicker it dissolves in water. All right, solubility on the other hand, so this is a lowercase s, referred to as solubility. Solubility is a measure, because there are units, so it's a measure of the amount. So a measure of the amount of solute that dissolves in water in a saturated solution. And since it's a measure, then the units are either grams per liter or more typically in moles per liter. And since you're doing calculations like that, you're going to be using your triangles mass over moles times molar mass, and you may also have to use the moles concentration volume relationship as well to do any calculations involving solubility. So they are the two definitions there that you need to know to start off with, KS and S. And then these two entities are interrelated, so you are often asked to calculate one from the other and vice versa. So what we'll take a look at now is there are three types of ionic solid that you need to know. We'll just get up a new page here. So three types of ionic compound that you need to know. I'm just going to split the page and we're going to derive some formulas here. So we'll just split it into three. Okay, so the first type is an AB type. An AB type ionic solid. And an example of this would be AgCl, so silver chloride. And the reason this is an AB type, this just refers to the ratio of cation is to anion. So you have one cation is to one anion. So AgCl is a good example. And what you simply have there is one silver ion ionically bonded to one chloride ion. The second type is an A2B type. An A2B type, a good example would be silver dichromate. There aren't too many examples of A2B types, but that's one there, silver dichromate. And what that looks like is you have your dichromate ion, and then you have two silver ions bonded to that. So that's an A2B type because the ratio of cation is to anion is 2:1. And then the third type you need to know is an AB2 type. And a good example of that would be lead bromide. solid, where you have one lead cation and then two bromide anions. Okay, so it's very important to determine which type of ionic solid you have first before you try to determine the Ks value or the S value for the solubility. Because then it follows that we can write an equation for the dissociation of each of these solids in water. So if AgCl dissociates in water, we don't need to include water in the equation because it's not reacting with it. It's just simply using its water wedges to break the ionic compound up into its ions. So Ag plus in this case, plus Cl minus. I'll write the state symbols in, though they're very important. So you start off with a solid and then dissociates into its two constituent ions. Now we can write a Ks expression for this. So just like we're writing Ka expressions for weak acids and Kb expressions for weak bases, and you can also write a Kw expression for the dissociation of water, we can also write the Ks expression for the dissociation of this sparingly soluble solid, assuming that it's now saturated. So the Ks expression is simply the concentration of Ag plus times the concentration of Cl minus. The reason we don't include the AgCl is because it's now considered to be a saturated solution, so its concentration is unchanging, so we just give it the value of 1, and therefore it's not in the expression. So the Ks expression is just simply Ag plus times Cl minus. Now, what we can do here is, if we want to relate Ks to S, there's a little trick we can do, and the secret to this is to say, let the letter S equal to the concentration, the starting concentration of your AgCl. And if we do that, then the Ks expression can now be changed to Ks is equal to the concentration of Ag plus ions, which you'll get 1S from that, and also you get 1S from the Cl minus. So what you have is S represents the concentration of Ag plus now, and S also represents the concentration of Cl minus, because you get 1 mole of each of those ions per mole of your starting ionic compound. So therefore Ks can be said to be equal to S squared. So if you're asked to calculate Ks from S, you can use this expression to start with, and then vice versa. If you want to work out S from Ks, then the square root of Ks will be equal to S. Now, some students don't learn those derivations, they just simply memorize this relationship here. So for the understanding, this is the derivation, and if you just want to remember this here, then you should be able to do any calculations interchanging between S and Ks for AB type solids. Let's take a look at the A to B type situation. So the equation here is going to be silver chromate solid dissociating in water. You're going to get 2Ag plus aqueous and plus your dichromate CrO4 minus aqueous. The Ks expression, we just line this up with the other one, so it's concentration of Ag plus, but it's now squared, and then it's the concentration of CrO4 minus. Using the same concept before, so in this case we're letting S equal to the solubility of the starting solid, so silver dichromate. Therefore, in this case, the Ks expression is going to read the concentration of Ag plus. Now you get 2 Ag plus ions for every 1 mole of silver dichromate. So if S represents this, then Ag plus is represented by 2S, and chromate is represented by S. So what we have here is Ks is now equal to 2S to be squared, because it's still squared here. All right. And then times S for the dichromate, so that becomes the Ks is now equal to 4S cubed is the relationship there. So Ks is equal to 4S cubed. That's the first thing you need to memorize then for an A2B type. And therefore, if you want to work out S from Ks, then you need to get the cube root of Ks divided by 4, and that will give you your S value. So that's the relationship for an A2B type. It also works out to be the same relationship for an AB2 type, and I'll show you here just to finish. So PbBr2 solid, that dissociates, it's going to give you Pb2 plus your Br minus, two of them, aqueous, aqueous. The Ks expression is going to be this concentration of Pb2 plus times the concentration of Br minus to be squared. And then again, if you let S, in this case, let S equal to the concentration of PbBr2, then the Br minus is going to be represented by 2S, because you get two of them for every mole of the compound, and then Pb2 plus is represented by S. So it's the same situation again. Ks is therefore equal to, in this case, S, which represents the Pb2 plus, and then the Br minus is 2S, and it's squared from the original expression. So again, the relationship here is Ks is equal to 4S cubed, and therefore if you want to isolate S from that, it's going to be the cube root of Ks divided by 4. So what you guys need to remember in short is that the relationship between Ks and S for an AB type solid is this first one here. If it's an A2B or an AB2 type ionic compound, then it's this expression right here. Okay, now that's really important because otherwise we can't tackle any calculations of Ks or S. So let's take a look at some examples. So I'll just do a simple question here. So two straightforward questions here just to review our point. So the first thing we need to identify, in the question it says calculate the solubility of silver dichromate. Well, we're looking to calculate S first of all, so the answer should be in moles per liter. That's the first thing we can say. We need to look at the type of solid we have, and we have an A to B type solid. Therefore, the relationship between Ks and S is that Ks is going to be equal to 4S cubed, and we want to get S in this case, so then it's going to be the cube root of Ks divided by 4, this value. So all we need to do is be competent with our calculator. If you put that into your calculator, it's the cube root of 1.2 by 10 to the minus 12 divided by 4, and if you do that successfully, your answer should be so the answer is 6.70 by 10 to the minus 5 moles per liter. All right, now the question continues here. So you now have a value for S that's equal to the solubility of the compound, and they're useful numbers because you can compare them to other ionic compounds and see which ones are the most soluble without having to do an experiment. Calculate the concentration of each ion present in silver dichromate. Well, the situation you have here, and I should have done this at the start, was to write my equation down. So you should always start by writing an equation for the dissociation of these solids. And what we have here is 2Ag plus aqueous plus dichromate. And what they're asking us here is, what would the concentration of each of these ions be? Well, you've already worked out the solubility of the compound. So this value here represents the solubility of silver dichromate. And what we were saying before about the value of S, you've got to look at the number of ions you get from the dissociation. So Ag plus is represented by 2S, whereas dichromate you just get 1S from the dissociation of your silver dichromate. So in short, the concentration of Ag plus is equal to 2 times S, which is equal to 2 times 6.70 by 10 to the minus 5. That should be minus 5 moles per liter, which comes to 1.34 by 10 to the minus 4 moles per liter. So that's the concentration of silver ions that you get from the dissociation of silver dichromate. And the concentration of dichromate ions is simply equal to S, because you only get 1 mole per mole of the original compound. So that'd be moles per liter. Okay, in this third question here, we're looking to calculate solubility product, or Ks, for barium hydroxide given the solubility value of 0.1 moles per liter. So we got to look at the type of compound we have, and this is an AB2 type. So therefore, to calculate Ks, it's simply Ks is equal to 4S cubed. And if you put that into your calculator, well, then you get a value for Ks of 4.00 by 10 to the minus 3, and it's unitless because it's Ks. There's one other type of question I wanted to do which was question 2 from 2009, so I'm just going to write it down. Okay, so this question is a little bit different than the other approach that we were taking before. In this case, they've given you the equation for the dissociation of silver chloride, and they've given you the Ks value of 1.56 by 10 to the minus 10. Now in this case, rather than asking you to work out the solubility for AgCl or for working out the Ks, what they're asking for is the concentration of one of the ions when the solid dissociates in solution. So it's a saturated solution, so we can write the equilibrium expression. So the equilibrium expression for this is Ks is equal to the concentration of Ag plus times the concentration of Cl minus. And that is equal to 1.56 because that's the Ks value. Now we use the old substitution, so let S equal to the concentration of AgCl to start with. So therefore S is equal to the concentration of Ag plus, and also S is equal to the concentration of Cl minus. The Ks therefore is equal to S squared, so S is equal to the square root of Ks, which works out to be 1.25 by 10 to the minus 5 moles per liter. So that will actually equal to your concentration of Ag plus, because we said S was already equal to the concentration of Ag plus. So that's actually quite straightforward. The next thing we want to take a look at, so let's go back to our original starting point. And our original starting point said we had 3 sections to cover. So we've done Ks and S calculations. The next thing to take a look at is predicting precipitation. So let's take a look at section 2 now, predicting precipitation. So section 2, predicting precipitation. Okay, so the best way to teach this concept of predicting precipitation is to just deal with this one question here. So this is a question we have a situation where we're trying to form a saturated solution of calcium fluoride. So our equation, equilibrium equation, would be calcium fluoride solid dissociating in water, aqueous, plus 2 fluoride ions, which are aqueous. Now, if this is truly at equilibrium, then the Ks expression, the Ks value rather, is equal to 3.4 by 10 to the minus 11, given here. And the rule is that if the IP is greater than the Ks, then you get precipitation. Now, what is IP? Well, I like to refer to IP as the Ks expression for a system where you're unsure of whether it's at equilibrium or not. So, simply put, we could write an IP expression for this calcium fluoride dissociation. It's going to be equal to the concentration of calcium. And we don't know if this is greater than, less than, equal to, or greater than the Ks. That's the question. So if it was less than the Ks, we'll get no precipitation. If it's equal to the Ks, then it is the Ks. And if it's greater than the Ks, then you get precipitation. So that's what we need to do. So the start of these questions is always to write an IP expression or Ionic product expression. So in order to be able to work out a value for IP, we need to know the concentration of calcium ions and the concentration of fluoride ions. And what they're doing here is they're just putting a little bit of a twist in the question, or a sting in the tail, and they're giving us a dilution factor to deal with. So we have 35 mils of 6.5 by 10 to the minus 3 moles per liter calcium nitrate mixed with 165 mils of sodium fluoride. So the concentration of calcium ions, we'll better just do it down here. So the concentration of calcium ions is equal to the 6.5 by 10 to the minus 3 moles per liter, and that's given to you in the question up here. So you take that, and you have 35 mils of that. So it's 35 mils over the total volume, which is 35 plus the 165, which is 200. And that gives you a new concentration, or dilution concentration, of 1.138 by 10 to the minus 3 moles per liter. We have to do the same then for the concentration of fluoride. its original starting concentration was 4.7 by 10 to the minus 5 moles per liter. Dilute that down, well, we had 165 mils in 200 mils, and that now becomes diluted down to 3.878 by 10 to the minus 5 moles per liter. So therefore we put these numbers into the IP expression, so the IP expression is now going to be equal to 1.138 by 10 to the minus 3 moles per liter. Take that by 10 to the minus 5 moles per liter, and the IP value then comes out as 1.72 by 10 to the minus 12. And the Ks value originally was, if we see up here, was 3.4 by 10 to the minus 11. So this is less than the Ks value, therefore you get no precipitation. And that's how you do those questions. So they're the main, that's the main type of question they can ask you for the IP Ks expression. The only way they can make it a bit more difficult is to get you to deal with the dilution factor. Now the last thing we need to talk about is the common ion effect. Okay, so the common ion effect takes you back to level 2 and Le Chatelier's principle. Okay, so the key point with the common ion effect, as the name suggests, is that the solubility, which is S, so the solubility S of a solid is reduced in a solution that contains a common ion. So let's take a look at an example. So say we have a solution of sodium chloride, so good old salty water. So say we have a solution of NaCl, and its concentration is 0.1 moles per liter. So NaCl, and then into that solution, so instead of it being pure water as you would normally have for making your aqueous system, we're now using salty water. And then we're going to try and dissolve our silver chloride solid. Okay, and in this case, I'm sure you can identify or spot what the common ion is between the two systems. We have the chloride ion is in common. And as a result of this, the silver chloride will be less soluble in salty water than it would be in pure water, less soluble than in pure water. We'll just quickly explain why. Hopefully you can see from last year, and you have AgCl solid, and the AgCl solid is trying to dissolve in the solution as much as possible. You want to get the chloride ions dissolved, dissociated as much as possible. Unfortunately, though, the chloride ions are being supplemented by the dissociation of the NaCl in solution. So as a result, according to Le Chatelier, you remember Le Chatelier's principle from last year, a system responds to undo the change to the system. Now the change to the system here is that you're trying to add more chloride ions to the system. So in order to undo that change, the equilibrium will shift to the left-hand side and result in more AgCl forming. So that's the theory behind what's happening. It's called the common ion effect. It could also be referred to as Le Chatelier's principle. And now we need to take a look at some sort of questions that you could get asked here. So write down a question, and we'll take a look at it. So here's a question: calculate the solubility of AgCl solid in the NaCl solution. Okay, to calculate the solubility, the new solubility of AgCl in this solution, S of AgCl is equal to 1.7 by 10 to the minus 10. Now this would be in pure water. Okay, so we can write a Ks expression as usual. Ks expression equals the concentration of Ag plus ion from MCl minus ions. Now here comes the important point. Originally we were told that we had a concentration of NaCl of 0.1 moles per liter, which means that the concentration of Cl minus is predominantly equal to 0.1 moles per liter as well. the little bit of Cl minus that we introduced from the dissociation of Cl, or from AgCl, is considered negligible. So this is a tiny amount. So as a result of that, we're just going to say that the concentration of Cl minus ions is approximately equal to the 0.1 mole per liter from the dissociation of the NaCl. And if we do that, and it's a bit of an assumption, but there's no other way to figure out an answer for this. So if we assume that the concentration of chloride ions is predominantly equal to 0.1 mole per liter, it's going to be a little bit greater with the addition of the AgCl. But if we do that, then the Ks can simply be arranged. So the Ks value, which we know, over the concentration of Cl minus will give us the concentration of Ag plus ions. And that will be, the original Ks value was 1.7 by 10 to the minus 10 divided by 0.10 will give us a value of 1.7 by 10 to the minus 9 moles per liter, which is equal to the concentration of Ag plus, which is equal to the solubility for AgCl, because S is also equal to the solubility of AgCl as it is to the concentration of Ag plus. So that's a tricky little question, but that is an overview of any of the types of questions you could get for solubility in level 3 aqueous systems. So take a look at lots of past paper questions and keep practicing them, and eventually you'll start to enjoy doing these types of questions.